Welcome to Extraordinary Concepts in Physics. Today, this lecture I'll be doing a quick overview, very thin overview of string theory. So my name is Robert Nemeroff, and this is Michigan Technological University. And also known as PhysicsX, you can find lots of these lectures on the web and at iTunes, our Starship Asterisk. You can find them through PhysicsX. There's a whole list of lectures there, and there's the slides there as well. If you can read this, you can go there, or you can just search for these terms on Google. You can go to iTunes, as I said before. So let's get to string theory. So first, I'll start at the bottom. I am not a string theorist. My understanding of this particularly deep topic may be flawed. I will do my best based on the few papers I've read and things I've heard. Still, string theory is quite interesting and might be the great hope of physics to combine the best hope to combine quantum theory and gravity. So as it says, it's an attempt to explain both gravitational and quantum effects in a single theory. So what it does, string theory, is it takes electrons and quarks, and for instance, and not as one-dimensional points, but now as two-dimensional strings. So as before, they were little points, and they could only translate and spin and have magnitude of mass. Now you can think of them as strings. And strings, they're two-dimensional objects, so you get lots more of things you can do with them. So one of the ways that I view string theory is as a way to create more free parameters in which you can explain more things. So it's a bucket of things that you can do, but it is constrained because if it is a string, strings act in very certain ways. So it has constraints, but it has more ways that it can act. Strings possess only length, and they don't have height, and they don't have width. They're usually posited these as several extra spatial dimensions besides the three well-known and time. They're generally considered to be part of an 11-dimensional thing called M theory now. So sometimes string theory itself is a term that's not always used. M theory is more used. One question that I've always wondered about and never really found addressed in detail is, if these are strings, what are they strings of? Formally, only gross attributes are considered: length, spin, energy, tension, as for background and background attributes. So one understanding I've come to, although I said before I'm not a string theorist, is that strings are made out of some sort of confined form of dark energy, not unlike the miniature versions of cosmic strings or domain walls. Cosmic strings might then be stretched versions of particle strings from the early universe. It seems to me to be possible. So there's some kind of fundamental energy form. That's what it's strings of, confined energy form. In general, branes, short for membranes, are more general than strings. There's something called a D-brane, which is string end with the Dirichlet boundary conditions. You can look that up. I should have linked that. P-brane, which is a black hole solution generalized to 11 spatial dimensions. And an NS5 brane is a 5-dimensional object that can mimic a magnetic monopole. So there's certain things you can do with strings. Branes are more general. There's also something, I don't know if I get to this, it's called the bulk, which is the general space of the higher spatial dimensional time. And if the bulk is different, branes exist in the bulk. So strings can be open or closed. I drew a closed one before. You can draw open ones. A closed string is a graviton. An open string is a photon, the way this theory works. Strings can have, as I've mentioned this, here's the things they can have. Strings can split and they can reconnect. And they're designed to have many more degrees of freedom, therefore there's more you can do with them than a point particle, and then you match those up with reality to confine the free parameters, the boundary conditions on the free parameters. And it has worked very well. String theories can explain most of classical mechanics, if not all of it, much of quantum mechanics, much of general relativity. So why aren't we teaching string theory in elementary school? Well, we'll get to that later. For a while, there appeared to be many different types of string theories, and people worked on them separately. Some people believing that they might be connected, but they were shown to be connected, and now, well, there's bosonic type 1, 2A, 2B, HO, HE. So these are the number of spatial dimensions, as many as 26, as little as 10. Details were that these 26 only described bosons, tachyons were destabilizing, supersymmetry between forces and matter. were all part of the other ones. And now I think most of these theories are all thought to be part of the same general, or flavors of the same kind of general theory. So you have a general theory called M-theory, and then given ways of describing it. For instance, you can describe quantum mechanics by matrices or by differential equations. They will all give you the same, take the same data and create the same predictions from it. So these string theories have different attributes, different ways of expressing themselves too, the same fundamental basis. String theory, another thing that defines string theory is beside the strings themselves, the strings can move through n-dimensional space-time. And with that, they create something called an action, and you find things about this action in order to determine what's allowed and not allowed for strings. So two types of action are usually debated: the Nambu-Goto action, simplest invariant action, and is shown to be simple but not all that useful, to my understanding. The Polyakov action, better is constrained by boundary conditions, involves string tension, and is more typically used. So in classical electromagnetism and general relativity, there are 3 spatial dimensions and 1 time dimension. These are empirically determined. We didn't sit down somewhere, no set of physicists sat down and solved this from first principles. In string theories, however, the number of dimensions is determined by things like potential energy and the need to make force-carrying particles, for instance photons, massless or nearly massless. So all of these new dimensions are in space, though, and not time. As far as I can tell, there's usually only 1 time dimension. Every now and then there's a paper saying there should be another time dimension, but it doesn't usually get much play. Adding spatial dimensions seems to help a lot, though. So what happens to these extra dimensions? How come we keep seeing only 3? So I can move up and I can move down, I can move up, I can move left, and I can move front, which is in the 3 spatial dimensions, but I myself don't appear to be able to move in any of these other dimensions. And the typical reason is because these dimensions are very small. They may be as small as the Planck scale, which is described in other lectures. They are what's called compactified. So you need small wavelength particles to fit in and see them. They're considered to be typically rolled up, meaning circular. Move in this direction and you quickly return to your starting point. Analogy is a garden hose, viewed from far away, might appear to be a 2-dimensional string. So if you moved on the garden hose, if you looked at the garden hose, here's the garden hose up close. If you move around on the garden hose, oh, look at that, you can move around. It appears to be a full spatial dimension. If you view it from very far away, then it just seems to be a string. Different number of dimensions. That's what I'm trying to get at there. Okay, as I said, very large dimensions, they can be called the bulk, describing the dimension. We live possibly on smaller dimensional boundaries between bulks, sometimes called branes, membranes between bulks. So one prediction is that gravity is much stronger on very small scales. This is important because it's actually a prediction of string theory, which we'll get into in a little bit. Because one sees leaking from the bulk. So that's gravity acts differently, usually, as described in string theories. So light and most particles are constrained to be on the brane. Gravity, however, is not and can spread out over all of the dimensions of the bulk. Acceleration due to gravity falls off as r to the d minus 1, where d is the number of spatial dimensions. This is one reason that gravity is weaker than electricity and magnetism. So string theory holds promise because it can explain things that are just empirically determined in regular, classical, and even standard variety quantum mechanics and gravity. You know, why gravity is weaker than electricity and magnetism, we don't know. Why particles, why the proton has several thousand times the mass of an electron, we don't know. Ultimately, some information has to be put in to get anything out. But one of the great hopes of string theory is it can get much more of these things out from relatively simple starting assumptions. There are things, the geometry can become quite complex in string theory, and that's why a lot of string theorists have a very strong mathematical background, some of them which can teach in math departments, some of which are in math departments. Some people consider string theory to be, in fact, a form of mathematics. People who do well in string theory sometimes win math awards. There's a lot of geometry and topology in string theory, and one of the key things that is discussed is called a Calabi-Yau manifold. So it's a three-dimensional, what's shown here is a three-dimensional projection of a multi-dimensional object having properties and symmetries inherent in a Calabi-Yau manifold. So that's taking dimensions and portraying them how they are perceived given assumptions in other dimensions. So one thing that many people have done is try to figure out what a tesseract looks like. So if you draw a square, so I'm on this thing, I'm constrained to be in two dimensions. So here I have two squares that are two dimensions, and if I connect them, I can create what looks like a three-dimensional cube. Now, if I take another three-dimensional cube, I might be able to connect them and create a four-dimensional tesseract projected into three dimensions, again projected into two dimensions. So things like that happen frequently in string theory. Okay, so this is something, is string theory falsifiable? This is one of the debates of the modern age. String theory is an extremely sophisticated, extremely beautiful theory, but is it useful? So string theorists are insulted somehow by this. Well, because who wants to be told that the last, how many years of your life isn't really doing anything useful? They've created something that can be, that can show a lot of normal physics. However, people are looking, what's the prediction? How can we better understand our universe? How can we build a better mousetrap? How can we better understand dark energy? How can we better understand the differences between masses of particles? How can we understand the fine structure constant? How can we understand many things? Tell us, string theory, tell us. And what happens is string theorists have lots and lots of equations that are very, very impressive and sophisticated, but they cannot make usually a unique prediction, usually saying that we need to better understand the string theory in the future. And it might well be that in some years in the future, string theory will be better developed, it will be better constrained, it will be able to be reducible to all the physics we know and make great predictions. Unfortunately, some people are getting fed up with it. They keep coming, we'll give you the predictions, the definitive predictions in the future answer. Some famous people have done so. Richard Feynman was not a big fan of string theory. Sheldon Glashow, Lee Smolin, the last one has published a book. There is, though, as I said, some string theories predict that gravity will be much stronger at very short distances. This is not, however, easily falsifiable. So you can't go and test this very easily. People are thinking of ways to try to do this, but there has been no definitive test as of yet. Okay, so with my last slide, I will quote one of the pioneers of string theory, someone who is considered to be one of the brightest people in the world and who understands physics the best in the world, and who is since he's a pioneer, believes in string theory, he would have a bit defensive in his statement because he hears the criticisms. Edward Witten, who's at Princeton Institute for Advanced Study, where Albert Einstein was, says, "I wouldn't have thought that a wrong theory should lead us to understand better the ordinary quantum field theories or to have new insight about the quantum states of black holes." So his point is that it's providing new insights. Here's how you can think about this. Here's how you can think about other really complex things. However, Jim Holt, who I actually don't know very well, but I found this quote on the internet and I liked it. He says, as published in the New Yorker in 2006, "For more than a generation, physicists have been chasing a will-o'-the-wisp called string theory. The beginning of this chase marked the end of what had been 3/4 of a century of progress. Dozens of string theory conferences have been held. Hundreds of new PhDs have been minted, and thousands of papers have been written. Yet, for all this activity, not a single new testable prediction has been made. Not a single theoretical puzzle has been solved. In fact, there is no theory so far, just a set of hunches and calculations suggesting that a theory might exist. And even if it does, this theory will come in such a bewildering number of versions that it will will be of no practical use, a theory of nothing." So he's looking at the other side of this. So will string theory become useful? It's certainly beautiful and very complex. It takes a long time to understand. We don't know. That may be decided in the future. And with that, I will ask you to keep Schrodinger away from your cat. Thanks. Only translate and spin and have magnitude of mass. Now you can think of them as strings. And strings, they're two-dimensional objects, so you get lots more of things you can do with them. So one of the ways that I view string theory is as a way to create more free parameters in which you can explain more things. So it's a bucket of things that you can do, but it is constrained because if it is a string, strings act in very certain ways. So it has constraints, but it has more ways that it can act. Strings possess only length. and they don't have height and they don't have width. They're usually posited these as several extra spatial dimensions besides the three well-known and time. They're generally considered to be part of an 11-dimensional thing called M-theory now. So sometimes string theory itself is a term that's not always used. M-theory is more used. One question that I've always wondered about and never really found addressed Welcome to Extraordinary Concepts in Physics. Today, this lecture I'll be doing a quick overview, very thin overview of string theory. So my name is Robert Nemeroff, and this is Michigan Technological University. And also known as PhysicsX, you can find lots of these lectures on the web and at iTunes. The great hope of physics to combine the best hope to combine quantum theory and gravity. So as it says, it's an attempt to explain both gravitational and quantum effects in a single theory. So what it does, string theory, is it takes electrons and quarks, and for instance, and not as one-dimensional points, but now as two-dimensional strings. So as before, they were little points, and they could also, our Starship Asterisk, you can find them through PhysicsX. There's a whole list of lectures there, and there's the slides there as well. If you can read this, you can go there, or you can just search for these terms on Google. You can go to iTunes, as I said before. So let's get to string theory. So first, I'll start at the bottom. I am not a string theorist. My understanding of this particularly deep topic may be flawed. I will do my best based on the few papers I've read and things I've heard. Still, string theory is quite interesting and might